and welcome to this video. In this video we're going to look at the practical where we're going to be determining the value of g by a freefall method. Now, as always with these practicals, different people will do this different ways. I'm going to go over a rough overview of two separate ways of how this practical can be carried out, and then I'll go into a little bit more detail on the analysis of this. Now, in order to calculate g by freefall, we need to know a few things. Okay, we're going to refer to this as the SUVATs. Okay, we need to know at least three of these things in order to calculate the acceleration, right? Now, which of these are easy to measure? Well, a distance is pretty easy to measure, so we'll be able to measure the distance that it's moved. So that's going to be our first starting point. We'll be able to measure time. Time is pretty easy to measure, and while measuring a velocity at any instant is pretty difficult, setting an initial velocity we could probably do. So this is the basis of this experiment. Now, if we've got SU and T and we're trying to get A, that means we're going to have to base this experiment off S is UT plus a half AT squared. Now, if we're trying to get a value for the acceleration here, whenever we do these practicals, we always want to get this into the form of y equals mx plus c. But in order to change this equation into this form, where m is proportional somehow to this acceleration, we have to get rid of this term, because this term also has a variable in it. It's not a constant term. It does depend on something. But this has a u in, so we must define that u needs to be 0 meters per second for both of these setups. That then reduces this to s is equal to a half at squared, which means I can say s is my y-axis, t squared is going to be my x-axis, and that makes half a my gradient. Okay, so my gradient should be somewhere about 4, 5-ish. Okay, now the first method that we can do is by an electromagnet. Now, an electromagnet, I would say, is probably the best method for this because it provides much more accurate readings and setting an initial velocity than the light gate method will, which is the second method. So how the electromagnet method works, let's give us some space. So the electromagnet method, we're going to start off by having a clamp stand on a table, and this clamp stand is there to hold this electromagnet. Okay, now an electromagnet is basically a loop of wire that behaves as a magnet or becomes a magnet when you put a current through it. So this means that we could actually hold a metal ball bearing up. So this is a metal ball bearing by this electromagnet. Okay, and this is actually very useful, because if we're holding this electromagnet, if we're holding the ball bearing via this electromagnet, all we have to do to ensure that our starting velocity is 0 is turn off the electromagnet, which is very easy to do. Okay, that means that this electromagnet is going to be connected to the timer. So this is the timer, and if this is on a table here, we need to have some sort of switch at the bottom of the height. So this height we can measure, and let's call that s. So s is the distance that it falls through, and this switch is also going to be connected to the timer. So when we turn off the electromagnet, timer starts. As soon as this ball hits this switch and closes the switch, the timer stops. Okay, this means that we basically each time just have to set s to be a specific value, and that specific value we're going to change. Okay, then we're going to alter s by maybe 0.1 meters, and let's say we want to do it, ideally we want the distances to be as large as possible. So if you can, I would say start at something like 1.5 meters and then make your way up to 2. but obviously there's limitations on the size of the room, the size of your clamp stand. So I would say maximum you could probably definitely do in a classroom is 1.5 meters. And then you would have to decrease that distance down to 1 meter. But I'm just going to say here, because obviously it depends on what equipment you have, you want to set S to be a specific value and then alter S by 0.1, and you want to get 6 readings. Okay, that's always the case. With these, you need to have at least 6 readings in order to get a more accurate line of best fit. Now, this means that we can then get a table which records S in meters, which is the distance that we're defining, that then records T in seconds, or depending on how accurate your timer is, you could do it in milliseconds. And then, because we've already discussed that we want our equation to be half AT squared, we need to calculate T squared, which would have units of seconds squared. And also, I would ensure that you also calculate your errors for all of these values. Okay, but this is your general table. You're going to record a value for S, and you're going to record a value for T. I'm going to split this into 3 columns because you're going to do each. So repeat each measurement of T 3 times, and then your average is what you're going to square. Average squared is T squared. Okay. Now, you will then have a column of S against T. Now, if we want the gradient to be a half A, that means S has to be on your y-axis and T squared has to be on your x-axis. So this is S against T squared. Now, when you plot all of these points, you're going to plot them with some error bars, and hopefully you're going to come up with a graph that will pass through 0, so that you can pass through all of these error bars. And the gradient of this graph, the gradient will be equal to a half G. Okay, therefore your value for this is going to be G is actually 2 times the gradient of the graph. Okay, and if you go over to the errors video, you also can calculate your errors on G. You could also calculate the percentage difference between your value and the expected value, and then all of this would then basically give you extra marks when you're writing your conclusion and evaluation. Okay, so this is the first setup. Now the second setup is almost identical. However, instead of using this fancy electromagnet and switch setup to be a timer, we'll use light gates. Now light gates are also a very good method of setting the time. But there is one drawback of this light gates method. So we're going to have a very similar setup. We'll have a clamp stand where the clamp stand is going to be connected to 2 light gates. Okay, so let's call this light gate 1, light gate 2. We're going to vary the distance between these 2 light gates, so the distance that it's actually traveled. But now we don't have anywhere to drop. We don't have any specialist equipment in order to drop it to ensure that the initial velocity is 0. This is where our uncertainty comes in. So the biggest uncertainty in this case is the fact that is U equal to 0. Because when a person drops a ball, it's very different to when a magnet lets go of a ball, okay? When a person drops it, there is every chance that you can put a slight acceleration on that, and it doesn't seem like much, but when you have that inconsistently across all of these readings, and you're doing a lot of readings because you're doing 6 distances 3 times each, so you're taking 18 readings. If you have a massive variation in the way you're applying a small amount of force, it's going to change your readings. So this is the biggest uncertainty in this case, but it means that you're going to have to hold your steel ball or your ball bearing just above the first light gate, and then hopefully drop it from U equals 0. Okay, you'll probably find that your measurements using this method will be less accurate than your measurements using the electromagnet method. But then what happens is you set S to 6 different distances, and then you record the same table that we did last time. So we record S in meters, we then record the time in seconds, which we are going to split up into 3. Now the light gate records the time, so you'll have to, the light gate will be connected to a data logger, and the data logger is just basically a small computer that can do all these simple calculations really quickly. So the light gate will connect these two, will be connected to the data logger. The data logger will store this information of time. You'll do this 3 times, then you'll calculate the average, and then the average squared will be t squared, which will be measured in seconds squared. And again, make sure that you are calculating the errors on all of your measurements. And if we end up with the same table of results, we're going to end up with a very similar graph of results. So we're going to get S and t squared, because S is equal to a half AT squared, provided that U equals 0. We're going to end up with some values with error bars as usual, and we should find that the gradient of this, when you perform this, you should find that your gradient, exactly the same as before, is a half G, and therefore your result for this experiment is G is 2 times your gradient, and then make sure you're calculating your errors on that value. Okay, so these are 2 methods in order to work out the value of G by a freefall method. Like I say, the electromagnet method is much more precise, purely based on the fact that you're just defined to have a 0 velocity, vertical velocity. Okay, so hopefully these 2 methods make sense. Hopefully you do something similar to this and not completely different, and thank you for watching.